Welcome back, students, to our final lecture of Chem 502. In this lecture, we're going to look at improvements that have been made in the past few decades to improve upon the Hartree-Fock model that we discussed last time. So the learning goals for today are to understand what a basis set is, as well as the difference between basis sets. So we'll discuss the names, the nomenclature behind these basis sets and what they're trying to do. We'll also look at the models that move beyond Hartree-Fock. And then we're also going to want to be able to understand why computational chemistry is valuable to us and what it's doing for us. So we'll start with a little bit of a recap from last time. Last time we discussed Hartree-Fock models, and we discussed that these models are inherently limited. So in order to make an equation that's solvable in the Hartree-Fock model, we ignore the electron correlation. Doing this using the effective nuclear charge approximation counts the electron correlation for both electrons. So we go through a calculation for electron 1 that gives some repulsion due to the other electron, and we get the same thing for electron 2, which is not how it would work if they were correlating their movement. This makes the energy more positive than it should be. And since the energies in chemistry are negative, we get smaller magnitudes of numbers. So if our energy should be negative 79, we might get something like negative 78.5, a larger number, a less negative number. The Hartree-Fock model is useful in some applications, and we saw some of those last time. We'll see a little bit more of those in class, but it doesn't work for others. So in this lecture, we want to try to figure out how we can move beyond this model to get more accurate predictions. We'll look at this figure here, which shows the two different avenues we can go down to improve our calculations. So on the x-axis of this plot is electron correlation. So we can see here this bar is talking about Hartree-Fock models that do a very poor job of counting the electron correlation. They don't completely ignore it, so they're a little bit here off the 0 point, but they don't do very much to talk about it. If we could increase the determination of the electron correlation, so get a complete solution for this, we would move further and further down this x-axis here. In the y-axis, we have the basis sets. So remember, we're using basis sets to approximate our orbitals. The more basis sets we use, the more accurate our orbitals are. And to get a complete basis set limit, we get into the actual orbitals that we have. And that would be moving down the y-axis here. So the Hartree-Fock model is just an electron correlation effective nuclear charge model, and you can use more advanced basis sets with it if you want, and we'll talk a little bit about that today. So you can get basically all down this y-axis with Hartree-Fock models. However, the goal, the place we're trying to reach, is the actual wave function, which is sitting out here at complete electron correlation and complete basis set. And getting closer to that is harder, especially in the electron correlation way. So we'll talk first about how we can use different models to attempt to account for the electron correlation. And then we'll talk about complete basis sets, or the basis sets that we can use to try to get to more accurate limits there of basis sets. We construct more advanced models to try to get closer to the true solution shown down here. There can be aspects that models have that make them more appealing in terms of being generally applicable. Some of these aspects are that they are size consistent. So if you double the problem by adding doubling the number of atoms, say, you should be double the error. They also would like to be variational. That is, we can vary them to minimize the energy like we saw with the Hartree-Fock model. And they also have to be applicable to real problems. So the Hartree-Fock model has all of these constraints despite its glaring inaccuracies. One last thing that's important to note is that any theoretical model needs to only take into account the number of types of atoms that are involved and the number of electrons in the molecule. So we don't want to do things like force our chemical intuitions onto molecules. We don't want to assume, oh, this bond angle should be like this bond length should be like this, carbon does this. None of that comes into play. Just simply the carbon has 6 protons and 6 neutrons, and it has 6 electrons. 2 of which are valence, and they interact in some way. So we're not putting our own bias on this, we're letting the models speak for themselves with math. Before I go on any further, I want to remind you all that the goal for this lecture is not to have an intimate understanding of the mathematics behind each of the models and basis sets that we're going to talk about that are improving upon our initial Hartree-Fock calculations. Rather, what we're trying to do is to appreciate the improvements that are being made and say qualitatively, okay, we're using this model because it describes the electron correlation a little bit better, and it kind of uses this idea to do it. So that's the focus is going to be on the ideas and not on the math that goes into these ideas. We'll start by briefly considering configuration interaction models. So the idea behind these is that if we wanted to exactly describe a molecule, we need to consider the ground electronic state and then also every possible excited electronic states. And if we could do that, we would have an exact description of the molecule. This is, of course, impossible. And in an attempt to move beyond the simple Hartree-Fock calculations, we use these configuration interaction models. And so what these do is they consider the ground state wave function, but then they also consider excited state wave functions by promoting electrons from the ground state to the excited state. If you thought about this for a little bit, you would realize that there are many, many possible excited states. So for example, if you have a carbon atom, you could promote any one of any 6 electrons to an excited state. It has any different place that it could go. So this is pretty complicated to do these sorts of things. We can't consider every possible excited state, considering every single electron. And so typically what's done is you go through what's called CIS, which is configuration interaction with a single excited state, or CID for double excited state, to talk about either promoting 1 or 2 electrons to their excited states. So our single electron is not good enough. It doesn't actually give any improvement upon Hartree-Fock calculations. The 2 does and is the most common one that is used. This method is not size consistent, since if you had 2 different systems, so say you're trying to make a bond between 2 atoms, the individual atoms could have 2 electrons being promoted, but then the new molecule with twice as many electrons can still only have 2 electrons being promoted. So it doesn't give the same result as 2 individual experiments. Another attempt to move beyond the Hartree-Fock model are called Molar-Plusset models, and these are usually abbreviated with MP2, where 2 is the second order Molar-Plusset models. You can do different kinds of orders as well. This is the most common one. What we do for these models is we recognize that the Hartree-Fock solutions are not exact solutions of the Schrodinger equation, but they are exact solutions for a Hartree-Fock equation. So we can use them to actually get exact solutions for something. Now, we hope that these models are close to the actual energy. That's kind of the idea. We talked about that before with the variational theorem. We pick a wave function that's close enough to the actual wave function, and our energy is close to the actual energy. So what the Molar-Plusset models do is we say, well, our actual energy is equal to our Hartree-Fock energy that we just calculated, and then we add a little bit, a small perturbation to get to the actual energy. And that's what this lambda v term is here. It's a small perturbation to the Hartree-Fock models to get to the real energy. And this is based on changes in the electron-electron repulsion in the excited states specifically. The last attempt we'll consider that moves beyond a Hartree-Fock model is the density functional theory, which gets this crazy acronym here. That's the most common form that it's used in. Density functional theory uses some experimental results in the form of properties of an electron gas of uniform density. This experimental result informs the model on how electron motion is correlated. If you remember back to when we first started discussing many electron atoms, we mentioned that there were Coulomb and exchange integrals that got the symbols J and K. So what we're saying here is that the total energy for the Hartree-Fock model is equal to the kinetic energy plus the potential energy plus these weird integrals that come out of the quantum mechanical calculations. The Coulomb integral was talking about how our electron interacts with a distant nucleus, but the K integral was this kind of weird thing that has to do with correlation. And we didn't have a good solution for it before. This experimental result with the electron gas gives us a measurement for how this Coulomb integral, or the exchange integral rather, might interact. So the density functional theory uses this data to approximate the K integral with this exchange integral that's coming from this actual experimental result. So this model relies somewhat on experimental parameters. We're talking about what electrons do, but it nevertheless is a very accurate model in terms of predicting the energies and so forth of quantum mechanical systems. And this model is one of the most commonly used models for modern computational chemistry. Besides improving the model, we can also improve quantum mechanical calculations by improving the basis set that we use. We've seen before that the better the trial wave function, the more accurate the predicted energy. The first kind of wave functions that were used were called Slater-type orbitals, and these were just simply the solutions based on the hydrogen atom, and you can recognize the functional form here. So these were first used, and of course they bear the most resemblance to the actual problem, the orbitals at hand. However, they lead to integrals that are difficult, if not impossible, to evaluate. So these challenge the program. The computers can't actually solve these integrals. It was realized that it can be much easier to approximate these with Gaussian functions that are easily solvable by computers. And these Gaussian functions have the following form. So we have a 1s orbital that would be made of the sum of many Gaussian functions. And while individual Gaussian functions are not very good at approximating these Slater-type orbitals, that's our actual wave function, you can see here that the sum of, in this case, 3 Gaussians does a pretty good job at recapitulating the hydrogen atom 1s orbital. Of course, this deviates most strongly in this area near the nucleus. So what has happened with these orbitals is that these constants, these A constants here and these N constants here, have already been optimized to give the best fit. So we have kind of these equations for 1s orbitals, 2s orbitals, 2px orbitals, and so forth, that are describing for every atom. These have already been optimized and are generally true for every atom. And what we change is the contribution of each of these things into a molecular orbital. So we say, well, we have all of these carbon atoms, they're making a molecular orbital, saying something like benzene. How much does each carbon atom contribute an orbital to our benzene? How do we get p and d orbitals? We simply can multiply by x, y, or z, or in the case of d orbitals, x squared or xy or xz, something like that, to turn these s-type orbitals into p or d-type orbitals. And like I mentioned before, we modify the contribution of every orbital to get a molecular orbital. And that's what's going on with these basis sets. And so these basis sets are called STO and then 3G often, which means Slater-type orbitals with 3 Gaussian functions describing them. So that is kind of the most simple basis set that we can use here, these Slater-type orbitals with 3 Gaussians. We could go into some more complicated basis sets that get a little bit closer to reality. So our Slater-type orbitals have 2 problems. One, they are spherically symmetric, the same kind of problem we always see when relying on the solutions to the hydrogen atom, whereas different atoms might not have spherically symmetric orbitals due to electron repulsion. And the other complication is that these orbitals are atom-centric, which you might think is a good thing, but when we're forming molecules, they need to be molecule-centric and centered around the molecules. So we get around these by a couple of changes that we make. The first one is a split valence basis set. And so the notation here for split valence is 3-21G, and in some cases 6-31G. These are the 2 most common forms used. So these model the core orbitals by 3 or 6 Gaussian functions, and the valence orbitals as a set of 2 different Gaussian functions. So we have one set of 2 or 3, and then a different set of 1. And so what this does is it allows the valence orbitals to be described asymmetrically. We don't just have one kind of set of p orbitals, but we have 2 different sets of p orbitals with either 2 or 3 and then 1 Gaussian function, which breaks that spherical symmetry up a little bit. To get them less atom-centric, we use polarization basis sets. And the notation here is you put an asterisk after your basis set here. So we could have a 631G asterisk basis set, which is using this split valence basis set. But then on top of that, it makes SP or PD hybrids. So this is most commonly going to be in the form of PD hybrids. We add a little bit of D character to the p orbitals. And you can see here, this p orbital is now no longer centered around the atom. It's kind of shifted over maybe between a bond if there's two bonded atoms there. And this can be thought of as either making hybrid orbitals, like I just mentioned, but it can also be helpful to think of this as mixing in the first derivative along with the orbital. This can be helpful by thinking of this in terms of a Taylor series expansion, and this allows us to even further improve upon the model if we want by adding in second, third, fourth derivatives, and so forth. Another commonly seen model has two asterisks, and the two asterisk is the same as having one asterisk, but it also has some sp hybridization in the hydrogen atoms. And this is important, especially if you have a model where hydrogen is reacting. So this poses a question that we mentioned last time as well, that if we have all these better models, why use the Hartree-Fock model in the first place? Why do we even use that at all? Why do I teach you about that in the beginning of class? In general, we use this because it is simpler. And the simpler the model, the shorter it takes to run. So in some cases, this is actually time dependent, and we need to have these simpler models to save time. If we want to run a really large, complex molecule, we can't do that with harder calculations in some cases. So sometimes the Hartree-Fock model is not accurate enough and we need to use more complicated models. Other times it's totally accurate enough for the purpose that we're using, and it will do the problem it'll solve the computational problem in a much shorter amount of time. So we can look through some tables from the book, and we'll spend more time on this in class. I'm not going to go through that much here, that show how these models do. And in general, we'll find that in some cases, the Hartree-Fock is good, and the density functional theory and the molar plusset models generally are a little bit better. And we can see that here in both of these cases. In some cases, like in homolytic bond association, which is the homework problem for today is, the Hartree-Fock models are total garbage, whereas the other models are pretty good on average. And we'll look through these and compare these more in class. I want to end by thinking philosophically about computational chemistry. So why would we bother doing computational chemistry in the first place? The answer is that there are a lot of chemical problems that we can't determine experimentally. So if we want to know exactly the transition state between some reactants and products, we can never measure that molecule. It doesn't really exist in the test tube. It exists very briefly and then converts back either to reactants or products. However, we can simulate anything we want in computational chemistry. You can go in and you could simulate, you could add 5 bonds to carbon and simulate that and see what you get. And this will allow us to view transition states, see what transition states are likely, and so forth. We could also do reactive species or just high energy species that are necessarily transition states. None of these are able to be probed experimentally, and we can study them computationally. There's other applications for computation that we've seen already in class that I'll mention briefly here. Quantum mechanical calculations allow us to actually visualize molecular orbitals in a way that we can't really do experimentally, and as well as the vibrational frequencies. So using Gaussian, we can get a nice view of what the vibrational frequencies for a certain model are, or the molecular orbitals for a certain molecule are. And these are really nice things that we can do easily with computation. So I'll conclude the lecture here. Essentially, what we're talking about is that we have these Gaussian basis sets that we can use to make atomic orbitals and molecular orbitals, and we can improve upon them by doing things like adding in polarization and split valence basis sets to break up their symmetry and so forth. The Hartree-Fock model can work pretty well for some applications, but in others we need more advanced theories. That's where the density functional theory and molar plusset come in. And in general, research is always a compromise between the best model that you can get and also the computational speed that you have. So you have to balance these two to actually get the right model for your research of choice. And one of the most fruitful uses for quantum mechanical calculations are to do things that we can't see in experiment. Now, it's important to note that in order to validate our computation, we have to compare to experiments. We don't just want to do the homolytic bond cleavage and say, oh, look, here's my homolytic bond cleavage. Because when we compare that to experiment, we see it's total garbage. So it's always good to have some sort of comparison for your model to experiment. We showed that earlier today, and we'll do that in class a lot. We'll go through these charts in more detail to figure out exactly how good these models are and how trustworthy their answers are. And so with that, I'll end here for our final lecture of Chem 502. And I'll talk about this with you guys in class, and then we'll move on next semester. So you get a couple weeks off, and we'll move on into thermodynamics.